Hi everyone. So today we will spend some time solving some problems related to LQR and also look at problems from different methods that we had devised or derived earlier and see what they mean in the context of solutions, right. So I'll just solve some 3 or 4 problems and I'll just post maybe a bunch of them online just for your own benefit. Okay. So let's start with the first one. That could be that. Okay, let's start with what happens in case of a scalar system. So I have x dot is a x plus b u. X is in R, and so is a, b, and u. Let me assume that the system matrix is stable by itself, and I have a performance index of the form 0 to infinity q times x square plus some r times u square, and as usual q and r are numbers which are greater than 0. Okay. So we need to find an optimal control law that will minimize this j. Next, say some control law of the form u equal to minus kx that will minimize the j. Okay. Now, okay, let's do first step by step and then relate to the general theory that we have derived earlier. So with the application of this control law, x dot will be a minus bk times x. Okay. And then if I substitute this u equal to minus kx into my cost function, this will be 0 to infinity q plus r k square x square and dt. Okay. Now let's just check what we did here, right. So we had this cost function which was more general, and what did we do is set something like this, right. Set the guy inside the integral to minus d by dt of x transpose px, and then we had a couple of justifications on why we were doing this kind of a choice, coming also from the invariance, the Hamiltonians, and so on, right. So we will stick to this and then see what this means in our context. Okay. So I have so once I do this, so what does it mean? That I am doing a q minus, so q plus r k square x square is minus twice p x x dot. So this will be minus twice p x dot is a minus bk, and the two x's will be x square. Okay. Now I can just rearrange all these two terms and I can write this in the following way: q plus r k square plus twice p a minus bk x square is 0. Okay. Now for this to hold for all non-zero x, what we require is the following: that is q plus r k square plus twice p a minus bk equal to 0. Right. This is just the scalar form of the Riccati equation that we derived. This one. Right. So a transpose p plus pa will be twice p and so on. Right. Okay. So so what is the objective now? So okay. So one more step is, okay, if I look at this equation, I can also write the equation equivalently as a Lyapunov equation for a closed loop system, right. So when is a closed loop system stable? So if we just look at the standard Lyapunov equation for stability, that will be that if there is any q which is symmetric and positive definite, for which I can find a symmetric positive a definite solution to this Lyapunov equation, then my system is asymptotically stable. Okay. So, that's the equivalent of that here in this optimality case would be something like this, and in the scalar case I can just write it in the following way: A minus bk times p plus p A minus bk is minus q minus rk square. Okay. Now, what do we need to do is find an optimal control law right. So, I am not just interested in finding a stabilizing control, the system is stable by itself. I am also not interested in just placing the eigenvalues at certain locations, which could just be solving a linear equation for k. So, I am finding an optimal control law here that will minimize my cost function. Okay. So, let us find. So, essentially I am finding what is the value of k. Okay. So, first thing is, when the system is stable, then x at infinity will be 0. Okay. So, now j, which is 0 to infinity q plus r k square x square dt. So, I am just taking it from here. This will be equal to the following: minus integral 0 to infinity d by dt of p x square dt. Okay. So, this will be what? This will be simply p x square 0, because x at infinity is 0. Okay. Now, to minimize, the value of j given some x0 with respect to k. Okay. So, what are we looking at? We are looking at a solution to the equation of this form: dp by dk equal to 0. Okay. So, p from this equation can be written as minus q plus r k square twice a minus b k, and then okay, dp by dk equal to 0. I will do all the math here, and that will turn out that this is p is r k over b, or in other words the k, the optimal control law k is p b by r, similar to what we had here, right. So, what was the optimal control law here? This r. So, in the scalar case, this will be b p over r. That is what we just derived here, right, in a very simplistic way. Right. Okay. So, we can also look at it in a slightly different way. So, if I take this equation q plus r k square plus 2p a minus b k equal to 0, I can write this as q plus twice p a plus square root of r times k minus p b by square root of r square minus p square b square by r equal to 0. So, okay, this will have a minimum when this guy over here is 0. So, that essentially means that this is k equal to p b over r. Okay. Now, this is what I derive, right. Now, what is the value of p? To find a k, I need to find what is p. Now, p can be found out by the so I substitute in this equation q plus q plus r k square plus twice p a minus b k equal to 0. I substitute for k, and what I end up with is, okay, what is k? This is q plus r p b over r square plus twice p a minus b k, that is p b over r equal to 0, and I end up with solving a quadratic equation of the form of q plus twice p a minus p square b square by r equal to 0, right. So, in this q is known to me, a is known, b is known, r is known, and I can find an appropriate p. Find the right p, which gives me a k, which can be used to compute the optimal control law u equal to minus kx. This is my optimal control law. Okay. In a way, in other way, I can also maybe just quickly differentiate this with respect to k, and then get the same relation, right. Okay, that's a very simplistic way of looking at it from a scalar system point of view. Okay, so let's move a bit forward and say, well, I have ax plus bu. X dot is ax plus bu with a of the form 0 1 0 0. Okay, so both of these problems I am just taking from the standard textbook of Ogata on basic control. So, assume u equal to minus kx is of the form minus k1 x1 minus k2 x2. Okay. And let us say, well, I have a little easier looking cost function to be minimized, that is 0 to infinity x transpose x dt. Okay, and for some initial condition x naught, I just say c and 0. Okay. Now, I want to minimize this cost function with the undamped natural frequency to be 2 radians per second, right. Okay. So, this is my problem statement, right. So, what is an appropriate u that will minimize this function and also place the closed loop pole such that the undamped natural frequency is 2 radians per second. So, substituting the control law u equal to minus k1 x1 into here, I find out first the characteristic equation with u is minus k1 x1 minus k2 x2. So, that will be, so I have x1 double dot plus k2 x1 dot plus k1 x1 equal to 0. Next, so this substituted here would mean that k1 equal to 4. Okay. So, essentially I am now looking at a minus bk of the form 0 1 minus 4 and minus k2. Okay. Now, first is well, when is a minus bk stable? Whenever k2 is greater than 0, a minus bk is stable. Okay. Now, again I will do the same exercise of computing what is the optimal control law. X transpose x dt is x transpose 0 p x 0, or so I have to find when is this optimal, when is this cost function minimized. This cost function is minimized. So, if I put for q equal to I, r equal to 0 into my Riccati equation over here, or even say over here, I get the following expression. I get A minus B k transpose P plus P A minus B k is minus I. Okay. Now, let me assume that P is of the form P 11, P 12, P 2, okay, this is symmetric. So, this will also be P 12. This will be P 22. Okay. So, I just write it in this equation, right. What is my A minus B k of the form is so A minus B k transpose would be 0 minus 4 1 minus k 2. I have P 11, P 12, P 12, P 22 A transpose P plus P 11, P 12, P 12 and 0 1 minus 4 minus k 2 is minus identity. This is minus 1 0 0 minus 1. Okay. So, I get now P in so I just have to solve for P 11, P 12, P 22 in form of in terms of k 2. So, what do I get is I just rearrange terms and go through some computations. P 12, P 12, P 22 is 5 by twice k 2 plus k 2 over 8, 1 over 8, 1 over 8, 5 over 8 k 2. Okay. The performance index is what J was equal to x 0 transpose P x 0, right. So, I just substitute for all these things where x 0 was of the form C and 0. So, what do I get here is 5 twice k 2 plus k 2 over 8 c square. Okay. So, to minimize j, I just do the following: dj by dk2 equal to 0, resulting in k2 to be square root of 20. Okay. And therefore, u is minus square root of 20 x 2, and then the minimum value of j therefore is, because I know p now, is c square. Okay. So, this is the minimum value of j. Okay. So, some straightforward steps of how to compute the optimal control law given a certain problem. Okay. So, the last problem for today we will do is the following. So, I will again do a standard second order system with A is 0 1 minus 2 1, B is 0 1, Q is 2 3 3 5, R is 1 over 4. Okay, and then of course, it's a infinite horizon problem as usual. So, I just again fix P as P 11, P 12, P 12, P 22, and I'll here again use the standard cost function that we have here, right. So, J is integral 0 to infinity x transpose q x plus u transpose r u dt. Okay. So, the optimal control law in terms of elements of P, that is P 11, P 12, P 22. How do I derive that optimal control law? That is simply over here, right. I know what is R, I know what is B, I know how the terms of P look like. So that will simply be I'll just skip the computations. So U would be minus 4 P12 x1t plus P22 x2 of t. Okay. And then now I again go back to the Riccati equation, which is this one. I look at what are the solutions. I am given Q, I am given R, and from that, so from the Riccati equation, okay, I'll skip all those computations, but what substituting what P will substituting for P or substituting for A, P, B, R, and so on will give me the following things. So I have 4 P12 square plus 4 P12 minus 2 equal to 0. I have a minus P11 minus P12 plus twice P22 plus 4 P12 P22 equal to sorry minus 3 equal to 0, and lastly I have minus twice P12 minus twice P22 plus 4 P22 square minus 5 equal to 0. Okay. So, I have three equations here. Solving this equation will give me this will give me P12. I can use that P12 over here to get P22 and then substitute here to get whatever is remaining, that is P11. Okay. I will just say this is a very standard process. So, the P that we get will look in the following way: 1.7363, 0.3660, 0.3660, 1.4729. Okay. Then I can plug this P into my optimal control law, right. So, that is, and then of course, all the steps will follow, that I just substitute for P here, and the J minimum will just be as usual half x transpose 0 P x naught, and that will be 7.9 whatever 9047. Okay. So, that is again I am just taking you through the process and see what that things that we learned yesterday mean. Okay. So, what we also learned yesterday was a very nice looking thing, right, of we asked ourselves questions: when can we solve this equation? Then we constructed something called a Hamiltonian matrix, and then a bunch of results which give me conditions based on this expression, which I said that the Hamiltonian H is said to be in the Riccati operator if a condition like this holds. Hs was the closed loop stability matrix, and so on. Okay. So, if I just quickly go through this, and then what I find is something nice here, right, where P was equal to V2 and V1 inverse. Okay. So, let us just write down this. So, P was V2 V1 inverse. Now, where does V2 V1 come? V2 V1 is the stable subspace. So, this vector V1 V2 was from the stable subspace of H. What do I know about H? That when a solution exists, then the dimension of its stable subspace is n, or that there is no eigenvalues on the imaginary axis, right. So, how does H look like? So, let us do this quickly, right. So, I will just quickly run show the MATLAB code. So, I have A from the problem statement as 0, 1, 2, 1, B of this form, R is simply 1 over 4, Q and so on. So H, I just write all the equivalent expressions for H and so on. Okay, so let's quickly do this. So I have A from my problem statement, which is like this. I have B, and I similarly define my Q and R as in the problem statement. I construct H in the following way, right? So this is how my H looks like. First, okay, let's just see what this thing here means. Right? So if I run this, okay, copy this and let me paste this here. Okay. So what I get is H, as in the theorem statement, has two eigenvalues which are positive and two eigenvalues which are stable. Okay. Now this this thing here, this with, so these two columns here, starting from the column, sorry, the column of this and column of this will be the basis for my stable subspace. Okay. And then the first two rows here, this and this, will be my will be the basis of the stable subspace, right. These two correspond to the stable eigenvalues, that is 0.403 and minus 0.403 and minus 0.85. Okay. So these two, the first two columns of U will now be my basis for the stable subspace. What is that? From the slides, I am just constructing these things. The first two columns of dimension R 2n cross n. In that case, it will be, in our case, it will be R 4 cross 2. So the first two columns, and then I split those first two columns as V1, which is 2 cross 2, V2, which is 2 cross 2. So V1 will be the first four elements of U. So V1, right. So this is V1, which is just the first four elements of here. Similarly, I have V2, okay, which is like these elements 0.03, which is like the last four elements of the first two columns. Okay. Now what was P? P from the formula was V2 V1 inverse, right. So let's just compute. So P is V2 times the inverse of V1. Okay. Okay. So what we have? Okay, this is good, right. So we have exactly the same P that we computed over here, 1.7, 0.3660 and so on. Okay. So exactly the same P, right. So this is another very nice elegant method of computing the P, right, which we started off with the question, when can I solve this and under what conditions does there actually exist a solution to the algebraic Riccati equation, or under what conditions can I actually find the optimal control law. So I hope these four problems or three problems and the third problem with two different methods will actually give you good insights on how to solve problems for the assignments and any future problems, if any. If you come across any interesting problems or something which you are stuck at, you can just post them online and we will be able to help you out. Thanks for watching.